All right, let's work through an example that illustrates the circular motion that occurs when a charged particle moves through a uniform magnetic field. Let's consider the case of a proton traveling at a speed of 2 times 10 to the 7 meters per second in a plane that's perpendicular to a uniform magnetic field that has a magnitude of 0.3 Tesla. What we want to do is we want to calculate the radius and the direction of the particle's resultant circular path here. All right, well, the first step is to draw a diagram, and we'll go ahead and make use of the figure that we already have. And we're going to pick some initial direction for the particle velocity. In this case, we're going to draw the particle moving to the right here, so that it is perpendicular to the B field, which we have drawn coming out of the board towards us. We therefore have a B field that is pointing out of the board, while we have a velocity vector that is pointing to the right. We can then apply the force right-hand rule, because magnetic force is equal to QV cross B. And we're going to use the right-hand rule, which means we're going to take our fingers and point them along the velocity vector and try and push it into the magnetic field vector, which means we're going to have to rotate our right hand upside down so that our pinky end of our hand is kind of facing the top of the page. And when we do that, our thumb ends up pointing downward so that we get a force vector that points downward. All right, so this right moving particle is going to be deflected downward, so that the motion is apparently in a clockwise circle. Right? We can proceed forward with this. We can double check that once we've deflected it to the point where it is moving downward, we can again use the right-hand rule with now a velocity vector that is pointing downward, a B field that is still pointing out of the board, and the result is a force vector that points to the left now, which is again towards the center of the circular path. All right, now that we have a pretty good sense of what's going to happen with this particle moving in a magnetic field, it's going to move in this clockwise circular path, we can go back and we can ask ourselves, what is the goal of what we are trying to solve here? And in this case, the goal is to find the radius of the circular path. The next thing we can ask is, what tools do we have to help us deal with uniform circular motion, which is what we have here. Well, remember from Physics 1A that centripetal acceleration is equal to v squared over r. If what we're trying to do is solve for r, then what we want to do is rewrite this equation so that it does solve for r. And we will get r is equal to v squared over centripetal acceleration. And we're going to hold on to that equation for our next step. We see now that if our goal is to find the radius of the circular trajectory, then what we need to have is the velocity, but we already have that, and the centripetal acceleration that's undergone by the particle. So what tools do we have to find the centripetal acceleration? Well, we've already used one equation that relates centripetal acceleration to velocity and radius, so we're going to need to find another equation. One thing we automatically think about when we think about acceleration is that accelerations are related to force by Newton's laws. We know that the net force is equal to the mass times the acceleration on the particle. So specifically, in this case, we're looking for a centripetal force, which will equal to the mass times the centripetal acceleration. And we can rearrange this to solve for the thing we need, which is the centripetal acceleration, in terms of the centripetal force and the mass. And so that's an equation that we can carry forward. Right, now for this to get us any further, we're going to need to know the mass of the particle. Oh, but that's easy because it's a proton and that has a known mass. And we'll need to know the centripetal force acting on the particle. So the question is, what is the centripetal force acting on the particle? Right. So stop and think and recall that centripetal forces are not new forces. So the centripetal force is not a new force. Instead, it is simply a relabeling of existing forces. So what forces are there in this problem? Well, the only force in this problem really is the force due to the magnetic field. Right? So we'll take the force due to the magnetic field, and we'll say that since that's the only force available, then that must be the source of centripetal force. So we can write force centripetal is equal to the force, and I think in our slides we term it as FB, where FB is the force due to the magnetic field. And we know that we've just been working with an equation that gives us the magnetic force in terms of the charge, the velocity of the charge, and the magnetic field that it is experiencing. In other words, force is equal to QV cross B, and so we can carry that forward. All right, so let's see where we're at. We know the magnitude of the B field. We know the magnitude of the velocity. We know the charge on a proton, which means we have full knowledge of the magnetic force, which means that we can relate that to the centripetal force on the particle. So we know the centripetal force. And since we know the centripetal force and we know the mass of a proton, that means we now know the centripetal acceleration that the charge feels. And if we know the centripetal acceleration and we know its velocity, then we can finally calculate the radius that we're looking for. So now it's just a matter of plugging in numbers. Working with the magnitude of the magnetic force, we can write that as QVB times the sine of the angle between the magnetic field and the velocity vector, but that is 90 degrees. Right, so this is 90 degrees. So sine of 90 degrees is 1, so we're just left with QVB. So let's go ahead and plug in some numbers. For Q, we have 1.6 times 10 to the minus 19 coulombs. For V, kind of draw a line here to make it a little cleaner. For the velocity, we had 2 times 10 to the 7 meters per second. And for the magnetic field, we can put in 0.3 Tesla. Multiplying that out in our calculator, we get 9.6 times 10 to the minus 13 newtons. And that's our magnetic force. Continuing on, we can take that value for the magnetic force, attribute it to the centripetal force, and plug that into the equation for centripetal acceleration, so that we get the centripetal acceleration is just equal to the centripetal force, which we just had, 9.6 times 10 to the minus 13 newtons. And we're going to divide that by the mass of a proton. The mass of a proton is 1.67 times 10 to the minus 27 kilograms. And plugging that into our calculator, we get 5.748 times 10 to the 14 meters per second squared as our acceleration. So we have this number now. And so finally, we can plug that centripetal acceleration into our equation for the radius right here and end up with R is equal to velocity squared. That's going to give us 2 times 10 to the 7 meters per second, the whole thing squared, over our centripetal acceleration, which is 5.748 times 10 to the 14 meters per second squared. And if we plug that all in to our calculator, we end up with a value of 0.696. Units all cancel except a meter up top. And so our final answer is that the radius of the circular path is 0.696 meters. Now, instead of plugging in numbers, it is also useful to work things symbolically. So let's go ahead and see if we can get a single equation that represents the radius of curvature given the known parameters. So we'll start from the magnetic force equation, and we can write that the magnitude of the centripetal force is equal to QVB sine of the angle between the two vectors. Then taking it back one more step, we can write the centripetal acceleration in symbolic form is going to equal to the centripetal force, which was QVB sine theta, divided by the mass. And then finally, we can write the radius of the circular path as being v squared over the centripetal acceleration, which we can write as QVB sine of theta, divided by m, so that the m comes up top. We notice that one of the v's here will cancel, so this v will cancel the square of the v here, which leaves us with mv over qb sine theta. And in the limit that we have the B field being perpendicular to the velocity, then sine of theta is equal to 1, and we end up with R is equal to M magnitude of V over Q times the magnitude of B. And that is our equation for the radius of curvature for this problem. And if, again, we just plugged in the numbers to this equation, we will end up with R is equal to 0.696 meters again. And that's it.